Thank you very much. My name is Hal Curtis. I am head of marketing at SatSearch, and we are hosting today's event with our good friends at VEOWARE SPACE. We're very grateful, as I say, that you could all spend the time with us today to hear about this this topic. I'm not going to give too much of an introduction on the topic or the company because the guys Jan and Julien are going to do that for you. But I just wanted to say a couple of housekeeping things. The chat function is open, as I say, if you would like to use it to discuss any of the topics with each other and or with one of the presenters, perhaps while they're not speaking. But the main thing is please do feel free to use the Q&A function at any point during today's demo. And I will then put those questions to our speakers at the end of the presentation proper, so as not to disrupt things, but I'm sure they can handle those questions and go back to material that was presented earlier on if required. So those functions, if you're not so familiar with Zoom in the webinar format, depending on how you have your screen set up, it should just be a case of hovering the mouse and then selecting the option at the bottom on the bar that appears down the bottom. So if there's any other questions you might have on the setup of the structure of the event, please do just address them to me in chat. But yeah, we would be very grateful to receive all of your feedback and questions on the presentation as it's given. And so without further ado, I would like to hand over, I believe it's Jan speaking first, Jan Smolders of VEOWARE SPACE. Thank you.
Great, thanks a lot, Hywel, and good afternoon, evening, or good morning to everyone on this webinar. Very excited to be here. So my name is Jan Smolders. I'm the commercial director here at VEOWARE, and I'm sitting next to our CEO, Julien Tallineau. And so together we'll handle this webinar today with you. So today on the topic is the benefits of in-orbit agility. And this is a little agenda that we put together. So very briefly, we go through the company profile. I'll talk about the agility technology that we are developing, a quick overview on products and services, and then we'll move towards what is agility, why agility, and we'll run through some numbers that we've calculated, let's say, on agility for optical missions and SAR missions specifically. And as Hywel mentioned, happy to answer any questions after the presentation. So regarding a quick overview on who we are as VEOWARE SPACE, so we're founded back in 2016. We're about 15 team members. Here you see a few of our core team members in one of our offices in Leuven. So we have offices in Belgium and the UK. So in Belgium, it's UK, it's Leuven and Brussels. We've just launched our first product in space. Very excited. 1st of April. We have our first product, and next one is coming beginning next year. I'll talk about that later. We were supported by the European Space Agency, and we received also financing from the European Commission just end of last year. Now, one slide more on our team. We're a small team, but we're very agile, just as our products. We're always looking for new talent, people that combine technical depth with a bit of business savvy and creative flair to solve problems every day that we might face, either technical or business-wise. VEOWARE in the news. We've got some traction in the news recently, of course, with our first product in space that we launched together with Nanoavionics, and we actually got some exposure in the Belgian news. We've also recently announced that we've got good telemetries from the wheel from our reaction wheel in space, and as we speak, we're actually doing first performance tests. We've also signed an agreement with D-Orbit for the launch of our next product, which is the CMG, which I will talk about in a few minutes. So the agility technology that we are developing here at VEOWARE SPACE. And first of all, why did we start to develop this technology? And as most of you know on this call, well, space has more and more importance and strategic importance for governments and companies all over the world. And being it from an urban planning perspective or monitoring energy or optimizing maritime routes, or agricultural optimization, or even up to military. There are different sectors and industries that need data from space or usage from space technologies, right? But it's more than just needing data. Decision makers actually need to know what is happening on the planet every single day. They need to know what is happening now, today, not last week or a few days ago, right? And for these decision makers, they are relying on this data coming from space, and they use satellites that are in orbit. However, the problem there is that the vast majority of these satellites in space are quite slow in maneuvering. They basically look down, they look nadir, and they just collect what they can see just right below them. And that's a missed opportunity because there's a lot of interesting targets out there for these decision makers to capture, right? And that's exactly what we want to do. We want to unlock the agility that customers need on a daily basis. How? By equipping satellites with some of our innovative technologies. And there are actually two product lines in terms of innovative technologies. First of all, there is our reaction wheels. And this is the one that was recently launched in April with Nanovionics as a high torque reaction wheel, state of the art, focusing on micro satellites, mini satellites. And then there is the control moment gyroscope, for which we are offering 10 times even better than the state of the art, and targeting roughly between 50 and let's say 500 kilogram satellites. So these are our two product lines that we are serving. I do have a little movie as well to further introduce the CMG, because that is particularly a very unique product in the market. And this is a quick video we created last year where we went to IAC, introducing the control moment gyroscope to enable satellites to do any maneuver that they desire. You see actually here the wheel being assembled. So for those of you who are still new to CMGs, it's like a reaction wheel. You have a flywheel that is spinning, and that is mounted on a rotating platform or a gimbal, and that's providing a torque which is up to 10 times more torque compared to a reaction wheel. We make them scalable, so you can have 4, 6, 8, 10, 12 in a cluster, offering high power efficiency, high torque, and low micro vibrations, enabling various applications, on which we'll talk about a few of them later today in this presentation. So quickly on the positioning in the market, we are a high agility company, so our reaction wheels are also high agility, high torque. So regarding our reaction wheels, we have 2 times more performance compared to market alternatives. So that means we can put our ability to put satellites in motion is 2 times more, so more performance, also at a lower power consumption. But then, of course, there is the CMGs. CMGs can bring 10 times more torque, 10 times more performance compared to traditional reaction wheels, and also doing that at a lower power consumption. Now, all of this technology is something that we've been developing over the last few years, particularly with regards to the control moment gyroscopes. Is something we've developed with support of the European Space Agency, and we've been doing a lot of de-risking, a lot of testing with them and their facilities, and also more and more in our house, in our office, in the clean room here downstairs, as we're running into the qualification campaign now for the CMGs. A bit more on the differentiators here. One of the unique things is that we developed this with off-the-shelf components, right? So compared to some traditional players in the market who typically serve their clients with custom-made products, we are really using off-the-shelf approach and a design that is offering short lead times up to 3 months with all our products. All right. In addition to that, we apply this concept of modularity. So these are all these actuators, we look at them as building blocks, right? So if you look at the scale, the x-axis is the satellite size, the y-axis is agility. So typically for low agility, you would you will be using reaction wheels, a certain cluster of reaction wheels, but actually we could combine different reaction wheels to offer different level of agility. Potentially you want, for example, more roll agility. So you want a stronger reaction wheel for the roll axis. Once you move up in size, we can actually add CMGs to that. So you could combine reaction wheels with CMGs, or maybe it's only CMGs. You can have 4 CMGs, you can have 5, 6, 7, 8 CMGs. There are different models of CMGs as well. So you can combine various models. So this shows really what we can do, any solution, basically any type of ACS solution that we can put together for the need of the client. And this makes it configurable, mass production, short lead times. And again, a few other pictures of how different clusters can look like in different orientations and different positioning. Again, they are individual modules, and a cluster could look like this, right? This is a movie of more than a year ago, maybe even 2 years ago, where we were doing some first tests, and you can actually see how nicely they're working together. Spinning, the gimbal is rotating, and that of course offers agility to satellites. A very quick overview on products and services, because I've been really talking about technology as such, but very quickly, what does this mean from company perspective? First of all, as a service, we do help people and companies to define their agility. And that's a little bit what we'll talk about later as well. So what does agility mean for a client? How can we maximize their productivity in space? How can we unlock off-nadir angles? How can we do state-of-the-art image collections like multi-point, multi-strip, and so on? So this is the type of knowledge that we can put into the partnership, let's say, with our clients to help them define agility. Once the agility is defined, then we start looking into what's the best possible solution for this. You can have wheels, of course, for 12U to 16U. I won't go through all the numbers. I do invite you to, for example, send me an email afterwards. I can provide you this presentation so you can get all the numbers. The reaction wheel here, just one number I want to pinpoint is basically look at the torque, right? So this torque max is up until 0.1 Newton meter for a momentum of up to 0.7 nms. If you go to the next slide, this is the CMG. It has a similar angular momentum, but it has 1.1 Newton meter. So here is the 10x torque that comes into play. And this one we're using for satellites between 50 and 250 kilogram. And then there is the bigger brother, which is the mini CMG, which is actually just right me on this on the table here. This is our biggest CMG so far, serving, let's say, satellites between 250 and 500 kilogram. And again, all of this can be clustered. Again, a table with some more numbers. I won't run through them, but it shows you what you can get in terms of momentum and torque when you cluster some of these actuators together. Now, enough about these products and services. Let's move on towards agility. And why agility? Why do we want in-orbit agility? First of all, what does that mean, agility, right? So in-orbit agility is actually just the ability to put a spacecraft in a certain orientation and to change that orientation very, very rapidly, okay? So changing the orientation is better maneuvering, is better productivity, right? So some of the use cases that you can see here is, first of all, rapid maneuvers allows better monetization. We can just do more work. We're just more productive. We waste less time in changing the orientation of the satellite. Point number two is that it actually allows new business cases and applications that you can enable with a satellite that is better maneuvering. And third is the faster reaction to events. For example, with collision avoidance events, you can just faster react to that. Supporting decision makers, as mentioned earlier. Why in-orbit agility? Again, because the market needs satellite imagery at the precise location as soon as possible and with the least clouds possible, of course, particularly for optical missions. And customers pay more for high spatial resolution, a high spectral resolution, a high temporal resolution, more coverage, and better data quality, right? So these are all the drivers that we see with our clients, being satellite manufacturers, but more particularly satellite operators, that they have this need, and they have a need for high agility to serve their end users, being again these data users or decision makers. Next, I want to give the floor to my colleague here, Julien, who will continue talking about what does agility particularly mean for optical missions and SAR missions.
Yeah, hello everybody. So I'm Julien Tallineau, the founder and CEO of the company, also an engineer from background. And I'm now also a substitute professor at University of Liège in Belgium, where I teach robust control engineering and control engineering for spacecraft. So even though I am basically running the company together with my colleagues, I keep a high passion for making sure our products are really meeting the user request and making sure that the products are themselves highly capable and state-of-the-art compared to what we see in the research field. All right, so high agility for optical mission, agility for SAR mission. Two extremely interesting topics, since they're both covering Earth observation, but in different ways. Optical is looking in the visible domain, as you know. Synthetic Aperture Radar, everything in the title covers the radar domain, and the two satellites don't look alike. Some satellites basically have a telescope, that's the optical satellites. The other, the SAR satellite, have an antenna. And of course, the dynamics of the two rigid bodies are different. So let's dive into the topics, shall we? So optical imaging is about 5 main operational modes, which is multi-point target, multi-strip target, stereo, 3-stereo, and of course, a bit of sun pointing here and there and ground communication. Today, we're going to look at 3 of them, specifically in the frame of agility. So multi-point target is about collecting small patches all over, which are extremely valuable, extremely, let's say, important, because you don't look at points where nothing happens. Usually you get requests to see stuff where there's likely something that happened, or you know something happened and you want to zoom in. So that it's extremely valuable square kilometer, extremely valuable pixels that customers are willing to pay for. And agility unlocks basically the ability to provide those pixels extremely quickly. So if we look at this, we call this tasking, and this offers short response time and high refresh rates. So let's look a little bit on how it works. Basically, a satellite, in the worst case, can look from left to right, to left, to right, etc., etc., as the satellite passes over what we call an area of interest. So let's compare a bit 4 reaction wheels, state-of-the-art, compared to 4 VEOWARE CMG. And let's learn a little bit more on how these things behave. So let's assume we are working with a small satellite of about a 10 kilogram meter square of inertia, and we're working with reaction wheels of 1 nms of momentum, 0.05 Newton meter of torque. And we basically look at what if we put them in a pyramid for the reaction wheels, or the same for CMG, so that eventually we get a cluster which both have 1.8 nms of momentum in pitch, roll, and yaw. So here I just compared the basics, and it has basics physics, right? I don't plan to teach you anything here. The reaction wheels will just be able to do the maneuver in about 20 seconds. So we do a 60 degrees from total left to total right, 60 degrees in about 20 seconds. With CMGs, I'm actually looking at the same time scale, and I invite you to look at the right part of the screen, where you can see the CMG can actually do the maneuver in 3 times less time. So that's where what we say with agility is literally unlocking 3 times more productivity. We're not kidding. The maneuvers themselves are done 3 times faster. So you have plenty of time to take more image. All right. On top of that, multi-point target is only tasking. So you may only look at small stuff when you need it. But there's another mode which is extremely important, is a multi-strip. The multi-strip is actually the ability to collect multiple strips next to each other. And this is happening mostly for, this is happening mostly for mapping. So, you know, satellites, they sometimes don't need to zoom on the target. They just want to collect as many square kilometers as possible. You know, like Google Earth eventually needs to refresh all the square kilometer on the planet, and somebody needs to collect those square kilometers. So there you go, mapping missions. And here, as much as you can map, the more revenue you're going to make. Or the shorter time you will complete your project to map a certain area of interest. And agility unlocks the ability to collect multiple targets because the satellite can actually go from the top of a strip to the beginning of the next strip much faster. All right, so this requires high slew speeds while remaining within the angles in which the lighting conditions are good. So let's do the same, comparing 4 reaction wheels and 4 VO CMG. Here, let's look at a slightly bigger satellite, so 15 kilogram meter square inertia, still the same wheels, the same orientations in the pyramid. And here I basically have 3 strips being collected next to each other. What you see here is the satellite is actually going through a few modes. In control engineering, we like to say, or imaging, we like to say that the satellite is imaging. That's the green color you see there. So it's literally the satellite flying from in its orbit. At the left part of the graph, the satellite starts its imaging session. And then it starts to image the first strip. Then there's the blue lines where you see the satellite being rotated to start the next strip. There is then some black lines, which is the stabilization time, extremely important if you want to have accurate and fine non-blurred imagery. And then you start again imaging, moving, settling, imaging again. And here what we discover is if we use reaction wheels, we are only able to collect 60 kilometers long strip. Why? Because basically as the reaction wheels finishes the 3 strips, the satellite is already past the target. Like the satellite is not in visibility of the target anymore. So if we use CMGs, it's changing the game. We're talking about something that can rotate much faster and basically can collect also much longer strips because it can keep the target in visibility for a longer time. So here, multi-strip also very useful. So you see that how we simulate stuff is not just basics mathematics when it comes to actual complex imaging strategies. So we limit imaging within 30 degrees in pitch, minus and plus. We start 30 degrees pitch to image the first target strip. And actually, we then finishes at minus 30 degrees pitch. We limit some satellites' acceleration to 5 degrees per second square, specifically when there's deployable solar panels, because we care about those, we don't want to break them. And we limit the speed of the satellite to 4 degrees per second with state-of-the-art star tracker, because we don't want to lose the attitude determination. And as you see, basically, in all the top graph, you have the off-nadir angles. We look at the accelerations, but also we look at a particularity of CMGs, which are singularity avoidance, which is why you see in the power profile on the left of the graph, the CMG, the actual CMGs being activated and measured in their power consumption. And it's not smooth because the CMG are themselves optimizing their trajectory as they move. All right, the last one, and I'm going to go a bit faster on this one. I basically go through stereo imaging. Stereo imaging, it means collecting the target twice. Why would we collect the target twice, you're going to say? Well, easy. We collect the target twice to start looking at 3D mapping. So 2D mapping is about maps, building stuff for Google Maps. But as some of you have been on Google Earth, you see that sometimes there's just buildings. And when we see buildings, we can look at line of sight analysis, mostly for defense applications, but yet paying customers willing to get those 3D maps worldwide. And it's good to have drones to do that over cities. But when we talk about the terrain at a global scale, so at Earth, at planetary level, satellites is just the only way to go. And again, you can then combine stereo imaging plus multi-strip, so multi-strip stereo, so you can really go in complexity. And again, agility there is key. How does this work? So again, we looked at a 15 kilogram meter square inertia satellite. We kept the same wheel for making sure we don't confuse anybody here listening to us. And what we realized is because the satellite literally needs to image, stop, break in the other way to start looking backwards and at the beginning of the strip, and again re-image the full strip again, we see that reactionals really suck at this. Reactionals are really not good at this, at least for the satellite we consider it. There's optimizations on satellites that can be done, of course, always. But when we use CMG, you see you can literally quadruple the amount of square kilometer you'd collect. So the target is really longer. So again, an application which is super valuable if you have satellites, if you want to move to a different kind of application for your imaging satellites. Okay, I'll move through this part where you can get the presentation later. Eventually, this has also related to a business case where each square kilometer has a certain price. And depending where you're selling panchromatic for multispectral bands or even higher multispectral bands, each square kilometer becomes more and more pricey. Stereo imaging is even 20% higher price than panchromatic mono. And all this means that if you take a satellite of 15 kilogram meter square and the current momentum and torque that I have advertised, you can really compute how much revenue potential you can unlock using CMGs. So if we're talking about let's say 15 minutes where your satellite is really in visibility of stuff that is useful, then basically you can start thinking about how many millions or revenue opportunity you are unlocking using CMGs. And those millions per day are, of course, things you're going to have to sell, or you're going to cross fingers that there's no cloud on it. So all of these revenue opportunities remain opportunities. A lot of cloud is happening, so 60% you can already forget about, but it all depends on where your customers are interested to look. Again, for SAR, different kind of animal, yet interesting. Here we basically look at 4 different operational modes: the strip map, the spotlight, and still some pointing and ground communication to downlink all the data you collected. For myself, I just focus on the spotlight. Spotlight is basically, again, when you chirp an enormous amount of power through your radar antenna so that you can get the finest resolution on the ground. And here we don't care about the clouds at all. So here, basically, spotlight can be done with electronically steered antenna, or can be done with simple agility. That's a trade-off that each satellite manufacturer is invited to do, and even to contact us to help basically to help you in your trade-off. We have already done that for other satellites, and we'd be very happy to do it again. Here in spotlight imaging, it remains for tasking as far as we see it. And again, requires high slew speeds, except that for radar, the integration time might be longer. The smaller the satellite you use, basically the smaller the antenna you may have, and therefore the longer the integration time you may require on your mission. So hence, here a little bit things to keep in mind, that taking one image can take 10 seconds, where for optical imagery it can take just a few milliseconds. Here as well, spotlight imaging is interesting because here we're not cloud limited. So we can take spotlight image really wherever we'd like. We have simulated here, for instance, something for one customer that wanted to go from left to right, left to right, left to right, with every time a parameter, a flexible parameter, which was the distance along track, which can vary. So the distance along track is how much distance are the targets separated geographically in amount, computed in terms of kilometers, for a maximum deviation of nadir that we kept at plus minus 30 degrees. And here we noticed something. We noticed that agility had a high impact on these along track, and the higher the agility, the shorter the distance, or the closer the targets could be located. So what we discovered is there is actually a very interesting phenomenon called a repeatable cycle. That means literally that the speed of the satellite and how fast it rotates can actually auto-compensate, so that you can keep going on imaging and imaging and imaging left and right without losing your actual target from visibility. So you basically, your satellite moves ahead, but you're also doing your image left, you move ahead, you take your image right, and you're back precisely in the same orientation or same attitude as your initial point. So you can literally do it again and again and again indefinitely. So that is a repeatable cycle, which only agility unlocks, because you're fast enough to rotate from left to right. And again, here, business case. So we see satellite synthetic aperture radar image are priced higher than a typical optical image. So up to 5K euro per image for a new acquisition. Now, this is top quality radar data. So all of this might be applicable for your satellites if you're using something else than a Cosmos SkyMet, but still a high value to those data. And we still understand that, for instance, if you have a 100 kilogram meter square satellite and you can use our VOCMG, basically we're talking about a big differentiator. The big differentiator is, with us, you can move from basically one target acquired per minute versus 2 targets acquired per minute. So you literally double your revenue opportunity base. You can literally collect twice the amount of image. And here we don't care about the clouds because radar can pass through the clouds. So here you can collect, and as soon as the targets you select make sense for your customer, we are here to help you collect it. So of course, these are big numbers. So again, generating a high amount of revenue per day, should it be with reaction wheels or with CMG, this relies still on satellite manufacturer and satellite operators to push all those pixels through the market, but yet the physics don't lie, and the physics doesn't lie. The CMGs and high torque reaction wheels are here to help you making more revenue. And this needs to be very clear. That's one of the main conclusions of this workshop and this webinar. So I'm extremely happy to hand my presentation here. We'll be waiting the floor for questions. Thank you very much. And thank you to my colleague Jan Smolders sitting next to me.
Great. Thank you very much to you both. That was really interesting. Thank you for going into the numbers in such detail and being so open really about the performance numbers and the potential impact on business models and things. So that's great. Thank you. I've got several questions for you here. So I've tried to sort of organize them from the technology side and going into the agility side and back to the technology side so that we don't focus too much on one area. And some of this was covered in part, but just wanted to, clarify a few points. So firstly, CMGs can work alongside reaction wheels or other actuators in the system.
Correct.
When they're used in such combinations, are the power and control systems and interfaces quite complex for the satellite integrator or the operators?
Let's put it this way. We have stumbled and we spent hours and hours preparing it for people. So if at some point customer want to combine them, we have everything ready for them. But indeed, it's highly complex. Your rotation device can literally exchange momentum to one another. So one device can literally deliver torque, and if you don't size the other one properly, it will recuperate the torque and start rotating instead of the satellite. So it's indeed complicated that they work together. But if you manage to combine the best of both worlds, then I think you're still winning, because you only pay for the best of each world. So should it be for reactionals for whatever you'd like in safe mode, and CMGs for high torque will make it work for you. That's how it works. However, I have to say that the way we work is we usually provide software libraries. So for flexibility reason, we have not designed yet our onboard computer for guidance, navigation, and control. That may come in the future. So at the moment, it's a whole library pack that we deliver in C, and that needs to run on the customer onboard computer. And the more complex it is, the more CPU resource it's going to use. So, and that comes the discussion and the trade-off.
Right, perfect. Yeah, that makes a lot of sense. So you need a picture of the satellite as a whole to understand the full agility requirements, because you need to know, it's not just a case of the CMGs, you need to know the other attitude, the actuators and systems.
Yeah,
so
yeah, indeed.
Absolutely. So which leads into my next question, which was, how do you go about testing and quantifying the agility of the satellite as a whole on the ground before launch? What do you need to consider for the engineers?
Well, to look at the agility as a design parameter, where we start and what we have started always was what is your collection planning? What is the amount of things you want to look at over an entire day? That directly translates, if you know the inertia of your satellite, or at least a range of inertia, we can start looking at how much momentum you need and how much torque you need to basically have the ability to point everywhere within the next 24 hours. And usually we're not at the optimal point. So either the torque is too high, and basically we don't use the device should be a reaction wheel or a CMG to its full potential. So there we make 1, 2, sometimes 3 iterations. It takes about a month and a half to eventually boil it down to making sure we have enough momentum in roll, pitch, and yaw, also including all the perturbances that needs to be accumulated over time, like atmospheric drag if the mission flies in low altitude, solar pressures is tiny less, so of course we look less at it, but and eventually we help converging to the right actuators. Then agility is also about making sure your operations are not compromised, because as I have not mentioned it, but every device that is rotating a reaction wheel or CMG needs to be desaturated. So this is also something we include. So we explain how often we would recommend to offload the CMG or the reaction wheels, and hence also depending on how frequent the customer would accept, how big the magneto-torquers needs to be. So that's what is all about the agility.
Okay, brilliant. That makes sense. Thank you. A question from the audience is, could you provide determination accuracy and stability if one was to use the VEOWARE CMG instead of a traditional reaction wheel? I know you gave some numbers on this.
Yes, so there's multiple things. Again, the reaction wheel or CMG has its own jitter spectrum. So as it comes down to highly accurate pointing and stability, you need to differentiate between the micro vibration that the CMG or the wheel will produce, so to make sure you don't have blurry images. Mm-hmm. And for this, our control engineer would be rather happy to help. And we've done it, and we can just pass the data, the test data that we've done on a Kistler table, and Jan will certainly take your requests. And then on the actual pointing, we have requirements on torque resolution, torque accuracy, which we would be happy to run by your request as well. So, and that's for, that should cover the entire attitude pointing error, low frequency and high frequency.
And I'm assuming the stability requirements are particularly important for the multi-point imaging applications you discussed.
As soon as the spatial resolution increase, we basically it follows on a more and more constraining requirements. What I can say is from the beginning we sized our CMG to be able to offer a high quality imagery data for 50 centimeters ground sampling distance optical, typical panchromatic for multispectral data. So 50 centimeters was our reference. And this is where we can still say that we offer basically less than half a pixel blur factor for those missions.
Great, thank you. Now, agility, as you've described it, as you've mentioned, essentially opens up new business models, new ideas, new concepts, and in some ways it feels like there's almost each type of agility is an order of magnitude more possibilities when you think of the creativity in the market on the Earth observation side that comes from the end user and demand side. When people come to you to VEOWARE to discuss new ideas and new concepts, what sort of questions and what sort of considerations do you have, or should they think about perhaps before discussing?
Usually customers come to us with a mapping mission. So they say, look, we want to maximize the amount of square kilometer we want, because the business case relies on how much we can sell. And they still consider tasking as an option. So for instance, 80% of their mission is actually mapping at low resolution. And then maybe 1 of 2 or 3 satellites in the constellation, they're only tasking, and they're bigger, higher resolution. That's one element. At constellation, it's definitely a trade-off. A second element is sometimes within the same satellites, they say, look, we're going to do mapping 50% of the time, and 50% of the time we're going to do tasking. And we basically have customer considering how much CapEx, how much investment satellite operators need to make to have a fully operated constellation with a refresh or revisit time of the order of 24 hours or 1 week. And basically the level of agility is extremely impacting that factor. If you have agriculture that needs about a 1 week revisit, well, the agility may be less of a constraint. If you want to revisit all the city every 3 days, agility will be super high. So it developed. Eventually, our company, I would say, has specialized in being vertically understanding the markets. And when a customer comes to us, even if it's not clear what agility is, we understand from the end use case down to the pixel, down to the requirements on the guidance, navigation, control, and down to the micro vibration that our motors are creating. So we vertically understanding what customers' concerns usually are.
Great, and you consider the entire data processing and downlinking and compression pipeline.
We try. But again, we are a startup. We are 15 people, so we don't have all the knowledge either. Usually customers is also very intelligent and is asking very relevant questions.
Yeah, absolutely. Oh, that's great. And we've had another question in the Q&A. For off-nadir images, it might be difficult for geometric correction, or geometric correction may be difficult. What is the maximum angle you recommend for off-nadir images?
Oh God, that depends on the camera.
Application dependent, camera dependent.
Okay. Here's what I can say. This could be outside of this presentation. I'll speak from experience as a satellite manufacturer engineer in a previous life, where I was actually in charge of very high resolution imagery satellites, like a next generation of satellites. And I would say, from what I've seen, 30 degrees is the max, specifically for line sensors, and specifically for line sensors which are extremely long, where you're going to have, let's say, the left part of the sensor, which has a larger geometric error than the beginning of the sensor. And this is even more increasing as you go off nadir. So I would say for 24,000 pixels wide sensors, I'd say 30 degrees is already on the edge. If you look at less pixels on your line sensor, you probably can live with 30 degrees. Also, I think the state-of-the-art high-resolution spy satellites like Worldview 3 and others, they don't allow anything else than 25 or 30 degrees. So that's probably a reason also for that.
Great, thank you. That's a great answer. Thank you. It was a difficult question to put you on the spot, so appreciate that. I think that's just about covered everything. Oh, we do have a question. Do you plan to be at ILA in Berlin next week?
The ILA, no, unfortunately not. So we're not planning to be there, no. But we will be in a SmallSat conference in Utah, and we will have also booths at the IEC in Paris and also the Space Tech Expo in Bremen, where on both of them we will actually also demonstrate the CMG technology. So we do invite everybody who's there in Paris or in Bremen this year to come to our booth and feel what 10x torque feels like in your own hands. So please come do and visit us.
Brilliant. Yeah, I would definitely advise people to do that, because just obviously those who are interested, it'll be a fascinating demonstration, but just for nothing else, there's very few aspects of space technologies that you can experience, firsthand, see and feel and touch. So this is a great one. So SmallSat in Utah, IAC in Paris, and Space Tech Expo in Bremen. Is that right?
Perfect. Yeah.
So anybody listening in the audience, do feel free to reach out to VEOWARE Space and get in touch and try and arrange a meeting, or come by to their booths at these events. I think we've pretty much covered everything there. I don't know whether you guys had any last comments you'd like to make, but we're at the time. So yeah, if you wanted to just give people a final message to go away with, very grateful to everybody for joining for this event, and to our presenters for giving us such great insights today.
Yep.
Yeah. Thank you all for joining, and feel free to reach out. My email is on the slide. Happy to share with you our slides and more information. Happy to set up any calls or meetings to discuss about your needs or your interests. And thanks again for joining today.
Yeah. Thank you very much, guys.
And thank you to from SatSearch. Thank you, everybody. Have a great rest of the day and rest of the week.